Pulsars are among the most fascinating and enigmatic objects in the universe, captivating scientists and enthusiasts alike with their sheer precision, immense power, and unique role in our understanding of the cosmos. These spinning neutron stars, the remnants of massive stars that have undergone supernova explosions, are cosmic lighthouses that emit beams of electromagnetic radiation, radio waves, X-rays, or even gamma rays, sweeping through space with astonishing regularity. To fully grasp the significance of pulsars and their mighty beams, we must delve into their origins, characteristics, mechanisms, and the profound impact they have on modern astrophysics. At their core, pulsars are neutron stars, which are themselves the remnants of stars that once burned with incredible intensity. When a star with a mass significantly greater than that of our Sun reaches the end of its life, it undergoes a cataclysmic explosion known as a supernova. During this event, the outer layers of the star are expelled into space, while the core collapses under the force of gravity. This collapse compresses the core to an extraordinary density, creating a neutron star. To put this density into perspective, a single sugar cube-sized piece of neutron star material would weigh about 1 billion tons on Earth. Neutron stars are extraordinary in many ways. They are incredibly small, typically only about 20 kilometers, 12 miles, in diameter, yet they can contain more mass than our Sun. This extreme compactness leads to gravitational forces so strong that the surface gravity of a neutron star is billions of times greater than Earth's. The intense gravitational compression also causes the rotation of the neutron star to speed up dramatically. Much like a figure skater pulling in their arms to spin faster, the collapsing core of a dying star conserves angular momentum, leading to the rapid rotation that is a hallmark of pulsars. The rapid rotation is only part of the story. What makes pulsars truly remarkable are their powerful magnetic fields. These magnetic fields are trillions of times stronger than Earth's and play a crucial role in the pulsar's behavior. As the neutron star rotates, its magnetic field generates beams of electromagnetic radiation along its magnetic poles. These beams are not aligned with the star's rotational axis, meaning they sweep across space like the beams of a lighthouse. When one of these beams crosses Earth's line of sight, we detect a pulse of radiation, giving pulsars their name. The discovery of pulsars dates back to 1967 when Jocelyn Bell Burnell, a graduate student at the University of Cambridge, first observed a series of regular radio pulses while analyzing data from a radio telescope. These pulses were so precise that they were initially dubbed LGM, short for Little Green Men, as some speculated they could be signals from an intelligent extraterrestrial civilization. However, further observations revealed that these signals were natural phenomena, marking the birth of pulsar astronomy. Pulsars are often described as nature's most precise clocks. Some spin hundreds of times per second, emitting pulses with such regularity that they rival the accuracy of atomic clocks. This precision makes pulsars invaluable tools for a variety of scientific endeavors. For instance, they can be used to test the predictions of Einstein's theory of general relativity, study the interstellar medium, and even detect gravitational waves. The regularity of pulsar signals has also led to proposals for using them as navigation beacons for interstellar spacecraft, providing a cosmic GPS system for future explorers. One of the most extreme types of pulsars is the millisecond pulsar, which rotates hundreds of times per second. These pulsars are believed to have been spun up by accreting material from a companion star in a binary system. The transfer of mass and angular momentum from the companion star increases the pulsar's rotation rate, creating a cosmic dynamo that emits pulses at mind-boggling frequencies. Millisecond pulsars are particularly useful for studying gravitational waves, as their incredible timing precision allows scientists to detect minute disturbances in spacetime caused by the merging of supermassive black holes. Another fascinating aspect of pulsars is their role in the universe's life cycle. As pulsars emit radiation and particles, they lose energy, causing their rotation to gradually slow down over time. This process, known as spin-down, eventually leads to the pulsar becoming a dead neutron star, no longer emitting detectable pulses. However, the energy emitted during a pulsar's active phase can have profound effects on its surroundings. Pulsars can power spectacular phenomena such as pulsar wind nebulae, where charged particles accelerated by the pulsar's magnetic field create glowing clouds of gas and dust. One famous example is the Crab Nebula, which is powered by the Crab Pulsar, a young and energetic neutron star at its center. Pulsars also provide a unique window into the fundamental laws of physics. The extreme conditions on and around pulsars, such as their immense gravity, density, and magnetic fields, cannot be replicated in any laboratory on Earth. This makes them natural laboratories for studying the behavior of matter and energy under the most extreme circumstances. For example, the interiors of neutron stars are thought to contain exotic states of matter, such as quark-gluon plasma or superfluid neutrons, that challenge our current understanding of particle physics. In recent years, the study of pulsars has entered a new era with the advent of advanced telescopes and detection methods. Radio telescopes such as the Square Kilometre Array, SKA, and space-based observatories like the Fermi Gamma Ray Space Telescope have expanded our ability to observe pulsars across the electromagnetic spectrum. These instruments have not only discovered hundreds of new pulsars but also revealed unexpected phenomena, such as pulsars that emit X-rays or gamma rays in addition to radio waves. These multi-wavelength observations are helping scientists piece together a more complete picture of how pulsars work and their role in the cosmos. One of the most exciting developments in pulsar astronomy is the use of pulsars to detect gravitational waves. When massive objects such as black holes or neutron stars collide, they generate ripples in spacetime that propagate across the universe. By carefully monitoring the timing of pulses from an array of millisecond pulsars, known as a pulsar timing array, scientists can detect the subtle changes caused by passing gravitational waves. This technique complements the work of ground-based detectors like LIGO and Virgo, offering a new way to explore the universe's most violent events. Pulsars are not just scientific curiosities, they also hold profound philosophical implications. They remind us of the incredible diversity and complexity of the universe, as well as the interconnectedness of its phenomena. The same physical laws that govern the behavior of atoms and molecules on Earth also dictate the formation and evolution of stars, the dynamics of galaxies, and the mysterious workings of neutron stars. By studying pulsars, we gain a deeper appreciation for the beauty and unity of the cosmos. In conclusion, pulsars and their mighty beams are a testament to the power and precision of nature. These spinning neutron stars, born from the ashes of supernovae, serve as cosmic lighthouses, laboratories, and clocks, illuminating the mysteries of the universe. As our understanding of pulsars continues to grow, so too does our ability to unlock the secrets of the cosmos, from the tiniest particles to the grandest structures. The story of pulsars is far from over, and their study promises to reveal even more about the nature of reality in the years to come. The exploration of pulsars continues to yield groundbreaking discoveries that deepen our understanding of the universe, pushing the boundaries of astrophysics and opening new avenues of research. At the heart of this progress is the relentless quest to understand the physics behind these remarkable objects and their applications in unraveling the mysteries of the cosmos. One of the key areas of ongoing research focuses on the structure and composition of neutron stars themselves. Despite their seemingly straightforward classification as superdense remnants of massive stars, the internal structure of neutron stars remains a profound mystery. At their cores, the densities are so extreme that matter exists in forms entirely unlike anything we encounter on Earth. Scientists theorize that the core of a neutron star may consist of exotic states of matter, such as a quark soup, where protons and neutrons dissolve into their constituent quarks. Alternatively, the cores could contain hyperons, particles that include strange quarks, or even more speculative forms of matter like boson condensates or strange matter, a state hypothesized to be more stable than regular atomic nuclei. To probe these possibilities, researchers rely on both observational data and theoretical modeling. Observations of pulsars in binary systems, where they orbit another star, provide critical information. By measuring the pulsar's mass and radius with extreme precision, scientists can constrain the equation of state, EOS, of nuclear matter, which describes how matter behaves at such high densities. Recent breakthroughs in this area have been achieved using the Neutron Star Interior Composition Explorer, NICER, an instrument aboard the International Space Station. NICER has provided detailed measurements of X-ray emissions from pulsars, allowing researchers to map their surface temperatures and infer their sizes. Another powerful tool in the study of pulsars is gravitational wave astronomy. When two neutron stars in a binary system spiral toward each other and eventually merge, they emit gravitational waves that ripple across the fabric of spacetime. The detection of these waves by observatories like LIGO and Virgo has already provided groundbreaking insights. For example, the famous event GW170817, observed in 2017, was the first detection of a neutron star merger and was accompanied by electromagnetic signals, including gamma rays, X-rays, and visible light. This multi-messenger observation confirmed that such mergers are a primary source of heavy elements like gold and platinum in the universe. Studying the gravitational waves from neutron star mergers also helps scientists understand the physics of matter under extreme conditions, offering indirect insights into the interiors of neutron stars. Pulsars also serve as exceptional tools for studying the interstellar medium, ISM, the vast expanse of gas, dust, and plasma that fills the space between stars. As the radio pulses from a pulsar travel through the ISM, they interact with the charged particles in the medium, causing a phenomenon known as dispersion. High-frequency waves travel faster than low-frequency waves, leading to a delay in the arrival times of different frequencies. This dispersion provides a cosmic fingerprint of the ISM's density and composition along the line of sight to the pulsar. By analyzing these dispersion effects, astronomers can create detailed maps of the ISM, revealing its structure and dynamics on both small and large scales. Beyond their utility as scientific tools, pulsars are also valuable in testing the fundamental laws of physics. One of the most intriguing applications is their use in probing the limits of Einstein's general theory of relativity. While general relativity has passed every test to date, it is still an incomplete theory, as it does not incorporate quantum mechanics. Pulsars in binary systems, especially those paired with another neutron star or a white dwarf, create natural laboratories for testing the effects of strong gravitational fields. The orbits of these binary systems can be measured with extraordinary precision, allowing scientists to detect tiny deviations from predictions based on general relativity. For instance, the timing of pulses from the Holz-Taylor binary pulsar provided the first indirect evidence for the existence of gravitational waves, earning its discoverers the 1993 Nobel Prize in Physics. Millisecond pulsars, the fastest spinning pulsars, have opened yet another frontier in astrophysics. Their incredible stability and rapid rotation make them ideal for use in pulsar timing arrays, PDAs, networks of pulsars monitored to detect gravitational waves from supermassive black hole mergers. Unlike the high-frequency waves detected by LIGO and Virgo, these waves are in the nanohertz range, corresponding to events that unfold over millions of years. PDAs are effectively a galactic-scale gravitational wave detector, with the potential to uncover the population and behavior of supermassive black holes in distant galaxies. Recent advances in radio astronomy have significantly enhanced our ability to study pulsars. The Square Kilometre Array, SKA, currently under construction, promises to revolutionize pulsar research. With its unprecedented sensitivity and ability to survey large portions of the sky quickly, the SKA is expected to discover tens of thousands of new pulsars, including rare and exotic types. This will greatly expand our understanding of the pulsar population, their birth and evolution, and their role in the broader context of galactic and extragalactic phenomena. In addition to radio telescopes, space-based observatories are playing an increasingly important role in pulsar research. The Fermi Gamma Ray Space Telescope has detected dozens of pulsars that emit gamma rays, revealing a population of gamma-ray-only pulsars that were invisible to traditional radio telescopes. These discoveries have shed light on the high-energy processes that occur in the magnetospheres of pulsars, where particles are accelerated to near-light speeds and emit intense radiation. Future missions, such as the proposed Einstein probe, aim to explore the X-ray and gamma-ray universe with even greater sensitivity, potentially uncovering new classes of pulsars and neutron stars. The study of pulsars is also driving advancements in technology and computation. The vast amounts of data generated by modern telescopes require sophisticated algorithms and machine learning techniques to process and analyze. For example, the search for pulsars in the dense cores of globular clusters or near the galactic center involves sifting through millions of potential signals to identify genuine pulsars. These efforts are not only advancing astrophysics but also contributing to fields like artificial intelligence and big data analysis. In the realm of speculative research, scientists are exploring the possibility of using pulsars for interstellar navigation. The regularity of pulsar signals makes them ideal as natural beacons, allowing spacecraft to determine their position with high accuracy. This concept, known as pulsar-based navigation, has already been demonstrated in principle by NASA's NICER experiment, which successfully used X-ray signals from pulsars to determine the location of the International Space Station. Finally, pulsars hold the potential to answer some of the most profound questions in science, such as the nature of dark matter and the origin of the universe's magnetic fields. Some theories suggest that interactions between pulsars and hypothetical particles, like axions or dark photons, could provide indirect evidence for dark matter. Similarly, studying the magnetic fields of pulsars may offer clues about how magnetic fields are generated and sustained on cosmic scales. In every sense, pulsars are more than just remnants of dead stars. They are dynamic, powerful, and endlessly intriguing objects that connect us to the fundamental workings of the universe. As research continues to push the boundaries of what we know, pulsars stand as a testament to humanity's enduring curiosity and our ability to unlock the secrets of the cosmos. The fascination with pulsars stems not only from their exotic nature but also from their profound implications for our understanding of physics, astrophysics, and the evolution of the universe. These celestial phenomena, though born in the fiery deaths of massive stars, are far from inert remnants. They are dynamic laboratories where the laws of nature are pushed to their absolute limits. As our technology advances, we are entering an era of pulsar exploration that promises to unravel mysteries we once thought impenetrable. One of the most intriguing questions surrounding pulsars concerns their magnetic fields, which are among the strongest in the universe. These fields can reach intensities of up to 10^1 Gauss, billions of times stronger than the Earth's magnetic field. These extreme magnetic environments lead to the creation of magnetars, a rare and highly energetic class of neutron stars. Magnetars are capable of releasing massive amounts of energy in the form of gamma-ray bursts and X-rays, often in catastrophic events known as starquakes. These quakes occur when the immense magnetic field distorts the star's crust, causing it to crack and release bursts of energy detectable from across the galaxy. Understanding magnetars not only sheds light on the physics of ultra-strong magnetic fields but also helps explain some of the most energetic events in the universe. One particularly puzzling aspect of pulsars is the phenomenon of pulsar glitches. Despite their incredible precision as cosmic clocks, many pulsars exhibit sudden, unexpected increases in their rotational speed. These glitches are thought to occur due to interactions between the pulsar's solid crust and its superfluid interior. The superfluid, a state of matter with zero viscosity, can decouple from the crust, causing a rapid transfer of angular momentum. Studying these glitches provides a rare opportunity to probe the interior dynamics of neutron stars, offering insights into the behavior of matter under conditions that cannot be replicated in any terrestrial laboratory. The connection between pulsars and gravitational waves is another area of active research that continues to captivate scientists. While the detection of individual binary neutron star mergers has already transformed our understanding of these cosmic behemoths, the long-term monitoring of pulsars through pulsar timing arrays, PDAs, holds the promise of detecting a background hum of gravitational waves permeating the universe. This background is thought to arise from the mergers of supermassive black holes in the centers of distant galaxies. Each pulsar in a PDA acts as a cosmic metronome, and deviations in their timing can reveal the passage of gravitational waves. Detecting this background would not only confirm the prevalence of supermassive black hole binaries but also provide insights into galaxy formation and evolution. The role of pulsars in the hunt for dark matter is another frontier that sparks the imagination. Dark matter, an elusive form of matter that makes up about 27% of the universe, has so far eluded direct detection. Pulsars, with their extreme environments, may offer a way to study dark matter indirectly. For instance, some theories predict that dark matter particles could accumulate in the dense cores of neutron stars, altering their properties in detectable ways. Alternatively, pulsars could emit gamma rays through interactions with dark matter particles, such as annihilation or decay. Observatories like the Fermi Gamma Ray Space Telescope are actively searching for such signals, which could provide the first concrete evidence of dark matter. Pulsars also serve as key tools in the study of cosmic rays, high-energy particles that constantly bombard the Earth from space. These particles originate from some of the most energetic processes in the universe, including supernovae and the winds of pulsars. By studying the spectra of pulsar wind nebulae, glowing regions of gas and particles accelerated by pulsar winds, scientists can gain insights into the mechanisms that drive particle acceleration to extreme energies. This research not only deepens our understanding of pulsars but also sheds light on the broader processes that shape the high-energy universe. The discovery of fast radio bursts, FRBs, enigmatic millisecond-long flashes of radio waves, has added another layer of intrigue to pulsar research. While FRBs are not directly tied to pulsars, their brief, intense bursts share similarities with pulsar emissions. Some theories propose that magnetars or highly active young pulsars could be responsible for at least a subset of FRBs. The study of these bursts, which originate from billions of light-years away, has become one of the hottest topics in astrophysics, offering a tantalizing glimpse into the workings of the distant universe. In addition to advancing our understanding of the cosmos, pulsars are inspiring technological innovations. The use of pulsar signals for navigation, for example, has already been demonstrated in space missions. By triangulating signals from multiple pulsars, spacecraft could determine their position with remarkable accuracy, even far beyond our solar system. This pulsar-based navigation is a cornerstone of proposed interstellar travel concepts, providing a robust and autonomous system for guiding spacecraft across vast cosmic distances. The future of pulsar research is set to be transformed by next-generation observatories. The Square Kilometre Array, SKA, once operational, will be the most sensitive radio telescope ever built, capable of detecting faint pulsars in distant galaxies and uncovering entirely new populations of these objects. Meanwhile, advanced X-ray observatories like Athena and gamma-ray instruments like the Cherenkov Telescope Array, CTA, will provide unprecedented views of the high-energy universe, allowing scientists to study pulsars and their environments in exquisite detail. Even as we expand our observational capabilities, theoretical research is pushing the boundaries of what we know about pulsars. Simulations of neutron star mergers, for example, are becoming increasingly sophisticated, revealing the complex interplay of gravity, nuclear physics, and magnetohydrodynamics. These models are helping scientists interpret observational data and predict new phenomena, such as the production of short-lived hypermassive neutron stars that may briefly form after a merger before collapsing into a black hole. Pulsars also serve as a poignant reminder of the interconnectedness of the universe. The elements that make up our planet and our bodies, such as carbon, nitrogen, and oxygen, were forged in the cores of stars and distributed across the cosmos in supernova explosions. Pulsars, as the remnants of these stellar cataclysms, are not only cosmic relics but also active participants in the ongoing cycle of star formation and evolution. Their powerful winds and radiation shape their surrounding environments, influencing the formation of new stars and planets. Ultimately, pulsars are far more than astronomical curiosities. They are cosmic beacons that illuminate the fundamental forces of nature, from gravity and magnetism to the behavior of matter at its most extreme. They challenge our understanding of the universe and inspire us to push the limits of technology and imagination. As we continue to explore these enigmatic objects, we are not only uncovering the secrets of the cosmos but also deepening our connection to the universe and our place within it. The study of pulsars is a testament to humanity's unyielding curiosity and our ability to transcend the boundaries of what we know, reaching ever closer to the ultimate truths of existence. Pulsars captivate us because they are not just remnants of the stars that came before us, they are engines of cosmic wonder, spinning faster than the eye can comprehend and emitting beams of energy that have traveled across eons to reach us. Their existence beckons us to understand the extreme, where physics bends, reality warps, and the universe reveals its most profound secrets. Imagine a world where time itself becomes elastic, warped by gravity so intense that a teaspoon of material weighs more than an entire mountain. This is the realm of pulsars, where the interplay of mass, energy, and magnetism creates phenomena that defy intuition. Pulsars are nature's most efficient power generators, converting the rotational energy of a collapsing star into focused beams of radiation that can span the electromagnetic spectrum. It's no wonder they are described as cosmic lighthouses, yet even this poetic description barely scratches the surface of their astonishing nature. But pulsars are not just powerful, they are precise. The fastest known millisecond pulsars rotate at speeds of over 700 times per second, with their beams pulsing with such consistency that they rival atomic clocks in precision. Scientists have tapped into this stability to explore the universe in ways previously unthinkable. By measuring minuscule shifts in the timing of these pulses, astronomers have begun detecting gravitational waves rippling across spacetime, caused by the mergers of supermassive black holes billions of light-years away. Every pulse from a distant pulsar carries with it a signature of the universe's history, a ticking metronome that spans cosmic time. The intrigue deepens as we realize that pulsars are messengers from the edge of the known. They thrive in environments so extreme that conventional physics teeters on collapse. The temperatures on a pulsar's surface can reach millions of degrees, while its magnetic field could strip atoms apart. Even light bends under the crushing weight of its gravity, giving rise to effects like gravitational lensing, where the pulsar's own photons curve around it, making it visible even from behind. One of the most compelling mysteries in pulsar research is the nature of their magnetic fields. The strongest pulsars, known as magnetars, emit bursts of energy so powerful they can disrupt satellites and ionize Earth's upper atmosphere, even from thousands of light-years away. These starquakes release more energy in a fraction of a second than our Sun emits in 100,000 years. Yet, magnetars are still poorly understood. Why do some neutron stars become magnetars while others do not? What mechanisms power their devastating bursts? Answering these questions could unlock the secrets of magnetic fields across the universe, from planets to galaxies. And then there are the glitches, those sudden, puzzling changes in a pulsar's rotation rate. These glitches are thought to be the result of the superfluid interior of the neutron star interacting with its rigid crust, releasing pent-up energy. Each glitch is like a seismic tremor on Earth, but on a scale so vast it could affect the spin of an entire star. These events give us rare glimpses into the hidden interiors of pulsars, where the laws of quantum mechanics collide with the macroscopic forces of gravity. Pulsars are also key to understanding how stars die and galaxies evolve. As they spin down and age, pulsars lose energy, eventually fading into obscurity. But in their active lifetimes, they shape their environments profoundly. Pulsar wind nebulae, created by the outflow of energetic particles from the star, are some of the most beautiful and dynamic structures in the universe. The Crab Nebula, illuminated by the Crab Pulsar at its center, is a prime example, a glowing cloud of charged particles stretching across space, powered by the pulsar's unrelenting rotation. But pulsars don't live in isolation. Some exist in binary systems, orbiting a companion star. These partnerships are fertile ground for astrophysical discovery. When a pulsar accretes matter from its companion, it can spin up, becoming a millisecond pulsar, a rejuvenated stellar corpse that now spins faster than ever. Binary pulsars also allow for the precise testing of Einstein's general theory of relativity. In these systems, the orbits are so compact and the gravitational fields so strong that relativistic effects become measurable. Tiny deviations in the pulsar's timing confirm the predictions of general relativity, such as time dilation and the emission of gravitational waves. Even beyond their scientific value, pulsars are reshaping our vision of the future. NASA has already demonstrated that pulsar signals can be used for spacecraft navigation, effectively turning these cosmic lighthouses into a galactic GPS system. Imagine a future where interstellar spacecraft chart their courses by tuning into the radio pulses of distant pulsars, navigating the stars with precision and autonomy. The universe itself becomes a map, etched in the rhythmic pulses of dead stars. As technology advances, so too does our ability to study pulsars in unprecedented detail. The square-kilometer array will allow astronomers to detect faint pulsars hiding in the most distant corners of the universe. High-energy observatories like the Cherenkov Telescope Array will probe the gamma-ray emissions of pulsars, uncovering the mechanisms behind their immense power. Machine learning algorithms are already being employed to sift through vast datasets, identifying new pulsars and revealing previously unseen phenomena. And yet, despite all we have learned, pulsars remain shrouded in mystery. Could they harbor clues to the nature of dark matter? Some theories suggest that pulsars might interact with dark matter particles, creating observable signals. Could pulsars be used to study the elusive axion, a hypothetical particle that could solve long-standing problems in quantum physics? Every new discovery seems to deepen the mystery, opening doors to questions we never thought to ask. Pulsars are not just scientific objects, they are gateways to wonder. They remind us that the universe is far stranger and more beautiful than we can imagine. They are proof that even in death, stars can shine brighter than ever, casting their light across the cosmos and enriching our understanding of existence. For every question we answer, pulsars pose 10 more, daring us to look deeper and dream bigger. The journey of studying pulsars is far from over, it is just beginning. These spinning remnants of ancient stars are more than celestial curiosities, they are the keepers of cosmic secrets, waiting to be unlocked by those bold enough to search. And as we peer deeper into the night sky, following the rhythmic pulse of these distant lighthouses, we are reminded that the universe is alive with discovery, and we are only just learning to listen. The allure of pulsars lies not only in their scientific significance but also in their ability to connect us to the universe's most profound and extreme phenomena. Each pulsar, in its rhythmic and unyielding pulse, tells a story of cosmic violence, survival, and the intricate dance of fundamental forces shaping the fabric of reality. As we continue to study these enigmatic objects, we uncover layers of complexity that challenge even the most established theories, opening new pathways to understanding the cosmos. One of the most tantalizing questions in pulsar research revolves around their formation. When a massive star ends its life in a supernova explosion, the core collapses into a neutron star. However, not all neutron stars become pulsars. Some remain as quiet, cooling objects, while others ignite into the brilliant, spinning lighthouses we know as pulsars. What determines whether a neutron star will become a pulsar? Is it the star's mass, its spin rate, or the configuration of its magnetic field? These questions remain unanswered, but they hold the key to understanding not just pulsars but the life cycles of stars and the broader processes that shape galaxies. The role of pulsars in the ecology of the galaxy cannot be overstated. As pulsars emit powerful winds of charged particles, they inject energy into their surroundings, influencing the formation of new stars and even planetary systems. In some cases, these winds carve out massive bubbles in the interstellar medium, creating stunning structures visible across vast distances. These pulsar wind nebulae are not just beautiful, they are laboratories for studying high-energy physics, particle acceleration, and the behavior of magnetic fields on cosmic scales. Pulsars also play a crucial role in the search for exoplanets. While pulsars are hostile environments for life as we know it, their extreme stability makes them excellent tools for detecting the faint gravitational effects of orbiting planets. In fact, the first exoplanets ever discovered were found around a pulsar, PSR B1257+12, in 1992. These planets, likely the remnants of a destroyed companion star, orbit their pulsar with incredible precision, providing a unique glimpse into the resilience of planetary systems in extreme conditions. The discovery of pulsar planets has opened the door to speculation about the nature of life in the universe. Could exotic forms of life exist on planets orbiting pulsars, shielded from the deadly radiation by thick atmospheres or magnetic fields? While this remains purely speculative, it underscores the endless possibilities that pulsars present for exploring the boundaries of what is possible in the universe. Beyond their astrophysical significance, pulsars challenge our understanding of the fundamental nature of reality. In the extreme environments of pulsars, where densities rival those of atomic nuclei and magnetic fields reach unimaginable intensities, the familiar laws of physics begin to break down. These are places where quantum mechanics and general relativity collide, offering a glimpse into the elusive theory of quantum gravity that scientists have sought for decades. By studying pulsars, we are not just learning about stars, we are probing the very foundations of the universe. One of the most exciting frontiers in pulsar research is the use of artificial intelligence and machine learning to uncover new pulsars. With modern radio telescopes generating terabytes of data every day, finding pulsars has become a task that requires advanced computational tools. Algorithms trained to recognize the unique signatures of pulsars in noisy data have already discovered dozens of new objects, including rare and exotic types that were previously missed. These discoveries are expanding our understanding of the pulsar population and revealing new insights into their origins and evolution. In recent years, pulsar research has also ventured into the realm of multi-messenger astronomy, where observations across multiple wavelengths and messengers, such as electromagnetic radiation, gravitational waves, and neutrinos, are combined to provide a more complete picture of astrophysical phenomena. For example, the detection of gravitational waves from neutron star mergers has been complemented by the observation of gamma rays and X-rays from the same events, revealing the complex interactions that occur during these cataclysmic collisions. Pulsars, as the remnants of such mergers, provide a critical link in this chain of discovery, helping scientists understand the life cycles of stars and the mechanisms that drive some of the universe's most energetic processes. As we look to the future, the possibilities for pulsar research are virtually limitless. With the advent of next-generation telescopes like the Square Kilometre Array, we are poised to uncover tens of thousands of new pulsars, including those hidden in the dense stellar environments of globular clusters and the galactic center. These discoveries will provide unprecedented opportunities to study pulsars in a wide range of environments, from the outskirts of galaxies to the crowded regions near supermassive black holes. In addition, advances in X-ray and gamma-ray astronomy will allow us to probe the high-energy processes that power pulsars and their magnetospheres in greater detail. Instruments like Athena, the Cherenkov Telescope Array, and proposed missions such as the Lynx X-ray Observatory will provide the sensitivity and resolution needed to study pulsars at the smallest scales, revealing the inner workings of these cosmic engines. The study of pulsars is not just about understanding the stars themselves, it is about unlocking the secrets of the universe. From their role in testing the fundamental laws of physics to their potential as tools for interstellar navigation, pulsars are windows into a world of extreme possibilities. They challenge us to think beyond the boundaries of our knowledge and to embrace the wonder and complexity of the cosmos. Pulsars remind us that the universe is a place of infinite curiosity and discovery. They are beacons of knowledge, guiding us toward a deeper understanding of the forces that shape our reality. As we continue to explore these enigmatic objects, we are not only expanding our understanding of the cosmos but also reaffirming our place within it, a place defined by curiosity, exploration, and the unyielding pursuit of knowledge. And in their steady, rhythmic pulses, we find not just the echoes of dying stars but the heartbeat of the universe itself. Pulsars are more than remnants of cosmic destruction, they are the silent yet commanding storytellers of the universe, drawing us into their orbit with mysteries as deep as space itself. They force us to confront questions that lie at the edge of human understanding, acting as keys to unlock the secrets of time, space, and even the origin of matter. What else might these enigmatic objects reveal? The answers could rewrite the story of the cosmos. One of the most mind-bending aspects of pulsars is their relationship to spacetime itself. Imagine a fabric so distorted by a pulsar's immense gravity that time moves differently near its surface. These distortions are not theoretical, they are measurable. In binary pulsar systems, where a pulsar orbits another star, the warping of spacetime causes the orbit to slowly decay, emitting gravitational waves as predicted by Einstein's theory of general relativity. These ripples in spacetime carry information not just about the pulsar but about the very nature of gravity itself. Every gravitational wave we detect is a message from the depths of the universe, a whisper from events billions of years in the making. But pulsars don't just test our understanding of gravity, they challenge us to rethink the building blocks of matter. Neutron stars are so dense that their interiors might contain exotic forms of matter that exist nowhere else in the universe. Some theories suggest that deep within their cores, the neutrons themselves break down into a sea of quarks, the fundamental particles that make up protons and neutrons. This quark-gluon plasma might hold clues to conditions that existed moments after the Big Bang. Could pulsars be relics not only of dying stars but also of the universe's fiery birth? The story of pulsars grows even stranger when we consider the possibility of strange stars. These are hypothetical neutron stars that have transformed entirely into strange matter, a theorized state where quarks combine in ways we've never observed. If strange stars exist, they would be among the most stable objects in the universe, and they might even emit unique signals, waiting to be uncovered by our telescopes. The discovery of a strange star would revolutionize our understanding of particle physics and force us to rewrite the rules of what is possible in the universe. Even the outermost layers of pulsars defy comprehension. Their surfaces are believed to be covered by a nuclear crust, a lattice of nuclei so tightly packed that it's stronger than any material on Earth. Beneath this crust lies a sea of neutrons, where matter behaves like a fluid under unimaginable pressure. As the pulsar spins, this crust occasionally cracks under the strain, causing starquakes. These quakes release bursts of energy so intense they can outshine entire galaxies for brief moments. Each quake is a reminder that even the most stable-looking objects in the universe are constantly in flux, their surfaces rippling with the echoes of their chaotic births. And then there are the pulsar beams, those mighty lighthouses that sweep through the cosmos. What powers them? Scientists believe these beams are driven by the interaction between the pulsar's intense magnetic field and its rapid rotation. As charged particles are accelerated along the magnetic poles, they emit radiation across the electromagnetic spectrum. But this model is far from complete. Why do some pulsars emit primarily radio waves, while others glow in gamma rays? Why do some pulsars flicker unpredictably, while others pulse with perfect precision? These questions hint at complexities in the pulsar engine that we are only beginning to understand. The beams themselves may also carry hidden messages. Researchers have discovered that some pulsars exhibit strange, quasi-periodic changes in their pulse timing and intensity. These variations could be caused by phenomena as mundane as changes in the pulsar's magnetic field, or as exotic as interactions with dark matter. Could the signals from pulsars hold clues to one of the greatest mysteries of modern science, the nature of the invisible matter that makes up most of the universe? Some scientists speculate that dark matter particles, if they exist, might accumulate in pulsars, subtly altering their behavior in ways that we could detect. If true, pulsars could become the universe's natural laboratories for probing this elusive substance. Pulsars also link us to the distant past and the far future. The precision of their timing allows astronomers to measure the movements of entire star systems and even galaxies. By observing pulsars, we can reconstruct the history of the Milky Way, tracing the paths of stars that formed billions of years ago. Pulsars also offer a glimpse of the universe's distant future, as they slowly lose energy and fade into zombie stars that persist as cold, dark remnants for trillions of years. What role might these eternal objects play in the endgame of the cosmos? Could they become the final witnesses to the universe's slow heat death, or might they harbor the seeds of new creation in some unknown process? Beyond their astrophysical significance, pulsars provoke deeper, almost philosophical questions about the nature of time and existence. A pulsar's spin represents the most precise clockwork nature can produce, yet it is inexorably slowing down, its energy bleeding away into the void. This interplay between permanence and impermanence mirrors the universe itself, a place where the unyielding laws of physics govern a cosmos in constant motion, forever changing and evolving. Pulsars remind us that even in the face of cosmic decay, there is beauty in endurance and precision, in the way these lighthouses persist against the vast indifference of space. And yet, for all their precision, pulsars hold surprises. Some emit sporadic bursts of radio waves that seem to defy their regular rhythms. Others suddenly change their spin rate, as if shifting gears in response to some unseen force. These phenomena, known as nulling and intermittent pulsars, hint at processes we don't yet understand. Could these irregularities be clues to deeper layers of physics, or are they simply artifacts of a chaotic universe? Every time we think we've solved the puzzle of pulsars, they present us with new riddles. The future of pulsar research promises to be as thrilling as its past. Advanced observatories like the Square Kilometre Array will allow us to detect faint pulsars hidden in the most extreme environments, near black holes, in dense star clusters, or even in other galaxies. These discoveries could lead to entirely new classes of pulsars, each with their own unique behaviors and secrets. Space-based detectors, like the proposed ELISA mission, will complement this work by observing the gravitational waves emitted by pulsar mergers, revealing the violent events that shape the cosmos. Pulsars also hold the potential to revolutionize space exploration. Their predictable signals make them ideal navigation beacons for spacecraft venturing into deep space. NASA has already tested this concept with the NICER experiment, which demonstrated that pulsars could be used to pinpoint the position of a spacecraft anywhere in the galaxy. In the future, Interstellar probes could navigate the stars using nothing but the rhythmic pulses of these distant lighthouses, making pulsars not just objects of study but partners in humanity's journey to the stars. In the end, pulsars are more than astronomical objects, they are symbols of the universe's resilience and ingenuity. Born from cataclysmic destruction, they emerge as engines of precision and power, bridging the gap between the macroscopic and the quantum, the ancient past and the distant future. They remind us that even in the aftermath of cosmic death, there is beauty, order, and purpose. As we continue to unlock their secrets, we are reminded of the boundless curiosity that defines us as a species, and the infinite wonders that await in the vast expanse of the cosmos. The study of pulsars is not just an exercise in observation but a deep dive into the fundamental forces and phenomena that shape the universe. These rotating neutron stars act as natural laboratories where conditions are so extreme that they allow us to test theories and conduct experiments that would be impossible to replicate on Earth. Every pulsar is a unique experiment, a cosmic machine whose behavior reveals the interplay of gravity, electromagnetism, quantum mechanics, and nuclear physics. One of the most captivating areas of research is the role of pulsars in detecting and characterizing gravitational waves. While instruments like LIGO and Virgo detect high-frequency gravitational waves from catastrophic events such as neutron star or black hole mergers, pulsars provide access to an entirely different frequency range, nanohertz gravitational waves. These waves are thought to be produced by supermassive black hole binaries orbiting each other in distant galaxies. To detect them, astronomers rely on pulsar timing arrays, PDAs, networks of precisely monitored millisecond pulsars distributed across the sky. Subtle variations in the arrival times of their pulses can reveal the passage of gravitational waves, stretching and compressing spacetime across vast cosmic distances. Recent breakthroughs in PTA research have already hinted at a gravitational wave background, a faint hum created by the combined signals of countless supermassive black hole binaries. This discovery is a milestone in understanding how galaxies evolve, merge, and grow over billions of years. Future studies could even map the locations of these binaries, offering unprecedented insights into the large-scale structure of the universe. Pulsars also help us study the behavior of matter under extreme densities. Neutron stars are so compact that a single sugar cube-sized piece of their material would weigh about 1 billion tons on Earth. The forces at work inside a neutron star compress matter to such an extent that atomic nuclei dissolve, leaving a sea of neutrons and possibly other exotic particles. Theorists have proposed that neutron stars might host quark matter or strange matter, states of matter composed of free quarks, or even strange quarks, a heavier cousin of the more familiar up and down quarks. To understand these possibilities, scientists rely on observations of pulsar mass and radius. The most massive neutron stars ever discovered, such as PSR J0740 plus 6620, challenge existing models of the equation of state, EOS, which describes how matter behaves under extreme pressure. Observations with instruments like NICER, Neutron Star Interior Composition Explorer, have provided precise measurements of pulsar radii, helping to constrain the EOS and refine our understanding of neutron star interiors. These studies not only probe the fundamental forces at work in the universe but also test our theories of particle physics under conditions unattainable in any laboratory. One of the most striking features of pulsars is their magnetic fields, which are trillions of times stronger than Earth's. These fields are responsible for the spectacular phenomena we associate with pulsars, including their beams of electromagnetic radiation. In magnetars, a subclass of neutron stars, the magnetic fields can reach up to 10^1 Gauss, creating some of the most violent environments in the universe. Magnetar flares can release as much energy in a fraction of a second as the Sun emits in 100,000 years, disrupting satellites and ionizing Earth's atmosphere even from thousands of light-years away. Recent studies have shown that these magnetic fields may decay over time, powering the X-ray and gamma-ray emissions observed from magnetars. This decay process, driven by the movement of charged particles within the neutron star, provides a unique opportunity to study the interaction between magnetism, matter, and radiation in extreme environments. Understanding these processes could have profound implications for our knowledge of magnetic fields on all scales, from planets to galaxies. Pulsars are also crucial for studying the interstellar medium, ISM, the vast expanse of gas, plasma, and dust that fills the space between stars. As the radio waves emitted by pulsars travel through the ISM, they interact with the charged particles in their path, causing effects like dispersion and scattering. By analyzing these effects, astronomers can map the density, composition, and structure of the ISM across the Milky Way. This work has revealed phenomena such as vast ionized regions around massive stars and turbulent filaments of gas shaped by supernova explosions. Pulsar observations are even helping to study the mysterious missing baryon problem, the search for the ordinary matter that seems to be unaccounted for in the universe. Another exciting development in pulsar research is the study of pulsar glitches, sudden changes in their rotation rates. These glitches are thought to result from interactions between the solid crust and the superfluid interior of the neutron star. In a superfluid, matter flows without friction, a property that arises from quantum mechanics. Glitches occur when the superfluid's angular momentum transfers to the crust, causing the pulsar's spin rate to increase abruptly. By studying these glitches, scientists are gaining valuable insights into the strange and exotic physics of superfluidity and how it operates under extreme conditions. Fast radio bursts, FRBs, a recently discovered phenomenon, have added a new layer of intrigue to the study of neutron stars. These millisecond-long bursts of intense radio waves are thought to originate from highly magnetized neutron stars, possibly magnetars, located in distant galaxies. Some FRBs exhibit repeating patterns, suggesting complex magnetospheric activity or interactions with surrounding material. The discovery of FRBs associated with magnetar-like bursts has strengthened the connection between these enigmatic signals and the extreme physics of neutron stars. The hunt for new pulsars continues to push the boundaries of what we know. Modern radio surveys, powered by telescopes like the Meerkat Array and the upcoming Square Kilometre Array, are uncovering pulsars in previously inaccessible regions, such as the dense cores of globular clusters and the crowded areas near the galactic center. These discoveries are shedding light on the population and distribution of pulsars, revealing trends in their birth and evolution. But pulsars do not merely exist as objects of study, they are also tools for exploration. One of the most promising applications of pulsar research is in navigation. Their regular pulses make them ideal beacons for spacecraft, offering a natural alternative to GPS for interstellar travel. This concept, known as pulsar-based navigation, has already been demonstrated in principle by NASA's NICER mission, which used X-ray signals from pulsars to determine the position of the International Space Station with remarkable accuracy. In the future, pulsars could guide humanity's exploration of the galaxy, providing a universal map etched into the fabric of spacetime. As we delve deeper into the mysteries of pulsars, we are reminded of the interconnectedness of the universe. These spinning remnants of stars not only illuminate the life cycles of massive stars but also provide clues about the origins of matter, the nature of gravity, and the evolution of galaxies. They bridge the gap between the microscopic and the cosmic, offering insights into everything from the behavior of subatomic particles to the dynamics of galaxy clusters. In their relentless, rhythmic pulses, pulsars whisper the secrets of the universe across vast distances and unfathomable timescales. They are cosmic witnesses to the birth, death, and rebirth of stars, carrying the echoes of creation itself. As our technology improves and our understanding deepens, we stand on the brink of unlocking even greater mysteries, guided by the steady light of these extraordinary cosmic lighthouses. The ongoing exploration of pulsars continues to redefine the boundaries of astrophysics, unraveling mysteries that challenge our understanding of the universe and inspiring new lines of inquiry. These extraordinary celestial objects act as beacons that not only guide our knowledge of star evolution but also serve as tools to probe the very fabric of spacetime, the behavior of matter under extreme conditions, and the hidden forces shaping the cosmos. One of the most fascinating aspects of pulsar research lies in their ability to act as cosmic probes. As radio waves emitted by pulsars traverse the vast expanses of space, they interact with the interstellar medium, ISM, in unique ways. This interaction leaves measurable imprints on the pulsar signals, such as dispersion, a delay in signal arrival due to the frequency-dependent effects of the ISM, and scattering, causing signal broadening or smearing. By analyzing these effects, astronomers can reconstruct detailed maps of the ISM's density, temperature, magnetic field structure, and composition across the Milky Way. These ISM studies have led to groundbreaking discoveries, such as the detection of turbulence within giant molecular clouds and the identification of hot ionized gas bubbles surrounding massive stars. By mapping these structures, scientists are uncovering how supernova explosions and stellar winds shape the galaxy, influencing the formation of future stars and planets. Pulsars, in essence, become tools for tracing the dynamic processes that govern the life cycle of the Milky Way. Pulsars also provide a direct link to the mysteries of magnetism on cosmic scales. Their magnetic fields, which are trillions of times stronger than those found on Earth, give rise to some of the most energetic phenomena in the universe. These fields accelerate particles to nearly the speed of light, creating intense beams of radiation and driving pulsar wind nebulae, expanding clouds of charged particles glowing in X-rays and gamma rays. The Crab Nebula, one of the most studied pulsar wind nebulae, continues to fascinate scientists as they investigate the mechanisms that generate its spectacular emission and intricate filamentary structures. Even more extreme are magnetars, pulsars with magnetic fields up to 10 superscript 1 Gauss. These fields are so powerful that they can distort the atomic structure of matter, breaking apart atoms and molecules. Magnetars periodically release gigantic bursts of energy known as soft gamma repeaters or giant flares. These events are so intense that, in rare cases, they can even affect Earth, disrupting satellite communications and ionizing the upper atmosphere. By studying magnetar outbursts, scientists are gaining insight into the physics of magnetic reconnection, a process that releases magnetic energy explosively and plays a key role in phenomena such as solar flares and auroras. The connection between pulsars and fast radio bursts, FRBs, has added yet another dimension to this field of research. While FRBs were initially detected as mysterious, millisecond-long bursts of radio waves from unknown sources, recent observations have linked some of these bursts to magnetars. This connection suggests that extreme magnetic fields and plasma environments around neutron stars might be responsible for generating FRBs. However, many FRBs remain enigmatic, with their origins and mechanisms of production still under debate. Some theories even suggest that certain FRBs could be signals from highly magnetized environments around black holes or from yet undiscovered exotic astrophysical phenomena. Another frontier in pulsar research is the study of their timing precision. Pulsars, particularly millisecond pulsars, are nature's most accurate clocks, with some maintaining a level of regularity that rivals atomic clocks. This remarkable stability allows scientists to use pulsars as tools for fundamental tests of physics. For example, the timing of pulsars in binary systems enables the precise measurement of their orbits, revealing effects predicted by general relativity, such as gravitational wave emission and time dilation. The Hulse-Taylor binary pulsar, PSRB 1913+16, provided the first indirect evidence for gravitational waves and earned its discoverers the Nobel Prize in Physics in 1993. The precision of pulsar timing also makes them indispensable in the search for gravitational waves from supermassive black hole binaries. These systems, formed when galaxies merge, emit low-frequency gravitational waves that ripple across spacetime. By monitoring an array of millisecond pulsars, collectively called a pulsar timing array, PDA, scientists can detect tiny distortions in spacetime caused by these waves. Recent data from PDAs, including the European Pulsar Timing Array, EPTA, and the North American Nanohertz Observatory for Gravitational Waves, NNOGRAV, have provided tantalizing evidence for the presence of a gravitational wave background, offering a new window into the processes that drive galaxy evolution. Beyond their astrophysical significance, pulsars are proving to be invaluable in the study of fundamental forces and particles. Neutron stars contain some of the densest matter in the universe, making them ideal laboratories for testing the behavior of matter at extreme densities. Theorists are investigating whether pulsars could harbor exotic forms of matter, such as quark matter or strange matter. These states involve quarks, elementary particles that make up protons and neutrons, existing freely rather than confined within particles. Detecting evidence of such matter would revolutionize our understanding of the strong nuclear force, one of the fundamental forces governing the universe. Some researchers even speculate that pulsars could provide clues to the nature of dark matter, the mysterious substance that makes up about 27% of the universe. Dark matter particles, if they interact with ordinary matter, could accumulate inside neutron stars, altering their observable properties. For example, the presence of dark matter could affect a pulsar's rotation rate, magnetic field, or thermal emission. By studying these effects, astronomers hope to uncover indirect evidence for dark matter, potentially solving one of the greatest mysteries in modern physics. The search for new pulsars is continually expanding, driven by advancements in technology and observational techniques. The Square Kilometre Array, SKA, the most ambitious radio telescope project ever conceived, is set to revolutionize pulsar astronomy. With its unprecedented sensitivity, the SKA is expected to discover tens of thousands of new pulsars, including rare objects in unexplored regions of the galaxy. These discoveries will provide an unparalleled opportunity to study the population, distribution, and evolution of pulsars across the Milky Way. In addition to ground-based telescopes, space-based observatories are playing an increasingly important role in pulsar research. Missions like the Fermi Gamma Ray Space Telescope and NICER have expanded our view of pulsars beyond the radio spectrum, revealing populations of gamma-ray pulsars and X-ray emitting neutron stars. Future missions, such as the proposed Lynx X-ray Observatory, aim to probe the high-energy universe with even greater sensitivity, unlocking new insights into the extreme physics of pulsars and their environments. Pulsars also hold promise for the future of space exploration. Their predictable signals make them ideal candidates for interstellar navigation. By triangulating signals from multiple pulsars, spacecraft could determine their position and velocity anywhere in the galaxy with remarkable accuracy. This concept, known as pulsar-based navigation, has already been demonstrated in principle and could become a cornerstone of future interstellar missions. Ultimately, pulsars are far more than relics of dead stars, they are windows into the deepest mysteries of the universe. From their role in testing the fundamental laws of physics to their potential as tools for mapping the cosmos, pulsars are at the forefront of discovery, guiding us toward a deeper understanding of the cosmos and our place within it. As we continue to study these extraordinary objects, we are not only unraveling the secrets of the universe but also uncovering new questions, ensuring that the story of pulsars, and our fascination with them, will endure for generations to come. Pulsars are, quite simply, among the most profound astrophysical discoveries of the modern era. They embody a paradox of extremes, objects so small yet so powerful, so ancient yet so precise, and so far away yet so intimately connected to the forces that shape the universe. As we push forward in pulsar research, the questions they raise deepen, becoming more intricate and entangled with some of the universe's greatest mysteries. One of the emerging areas of study is the role of pulsars in the birth and evolution of stellar systems. When a massive star explodes as a supernova, the pulsar that remains can either be isolated or part of a binary system. In binary systems, the interactions between the pulsar and its companion star are particularly fascinating. Over time, the pulsar may accrete material from its companion, forming an accretion disk and spinning up to become a millisecond pulsar. This process, sometimes referred to as recycling, creates some of the fastest spinning pulsars we know, with rotational speeds exceeding 700 revolutions per second. These systems provide unique opportunities to study the transfer of angular momentum and the physics of mass exchange in extreme gravitational environments. Moreover, binary pulsars are essential tools for studying general relativity. Systems like the double pulsar, PSR J0737-3039, where two pulsars orbit each other, allow for precise measurements of relativistic effects. In such systems, phenomena like gravitational time dilation, orbital decay due to gravitational wave emission, and Shapiro delay, caused by the curvature of spacetime near massive objects, can be directly observed. These observations not only confirm the predictions of general relativity but also provide constraints on alternative theories of gravity, helping refine our understanding of the fundamental forces of nature. The link between pulsars and black holes is another tantalizing avenue of research. While no pulsar has yet been observed in orbit around a black hole, such a discovery would represent a major breakthrough. A pulsar black hole binary would allow scientists to test the limits of general relativity in the strongest gravitational fields possible. Observing the pulsar's timing signals as it orbits the black hole could reveal intricate details about spacetime near the event horizon, including potential deviations from Einstein's predictions. The search for such systems is ongoing, with large-scale pulsar surveys combing the sky for this elusive pairing. Pulsar timing is also being used to probe the distribution of dark matter in the galaxy. Dark matter, which does not emit or absorb light, reveals its presence only through its gravitational effects. By analyzing the motion of pulsars within the Milky Way, astronomers can infer the distribution of dark matter in the galaxy's halo. Pulsars in globular clusters or near the galactic center are particularly valuable for this purpose, as these regions are expected to have high concentrations of dark matter. These studies not only enhance our understanding of pulsars but also contribute to the broader effort to unravel the nature of dark matter, one of the most enduring mysteries of modern astrophysics. Another exciting application of pulsar research is the use of their signals to detect cosmic phase transitions. In the early universe, as it expanded and cooled, it likely underwent several phase transitions, moments when the fundamental forces of nature, such as the strong and weak nuclear forces, separated or changed behavior. These transitions may have generated gravitational waves, leaving imprints on spacetime that persist to this day. Pulsar timing arrays, by monitoring the precise timing of millisecond pulsars, could detect these relic waves, providing a glimpse into the universe's earliest moments, less than a fraction of a second after the Big Bang. The detection of fast radio bursts, FRBs, has added another layer of complexity to the study of neutron stars. While some FRBs have been definitively linked to magnetars, others remain mysterious, with no clear connection to known astrophysical objects. Some FRBs exhibit strange periodic patterns, suggesting highly organized processes, while others are completely random. The discovery of repeating FRBs adds further intrigue, raising questions about whether they are produced by young, highly magnetized neutron stars, collisions, or entirely new astrophysical phenomena. Pulsars and magnetars provide a natural connection to FRBs, as their extreme magnetic fields and dynamic environments are capable of producing the short, intense bursts of radio energy that define FRBs. As we probe deeper into pulsar environments, we are beginning to uncover their role in particle acceleration. Pulsars are natural particle accelerators, capable of driving particles to energies far beyond those achieved in Earth-based experiments like the Large Hadron Collider. The charged particles ejected in pulsar winds interact with magnetic fields to produce high-energy radiation, including X-rays and gamma rays. Observing these emissions not only provides insights into the physics of particle acceleration but also helps us understand the origin of cosmic rays, the high-energy particles that bombard Earth's atmosphere from space. On an even larger scale, pulsars contribute to the broader study of galaxy dynamics. Their distribution across the Milky Way reveals patterns of star formation, supernova activity, and the movement of stellar populations over billions of years. Pulsars in globular clusters, dense collections of ancient stars, provide clues about the conditions in these environments and the processes that lead to the formation of compact objects. Meanwhile, pulsars in the galactic halo offer insights into the history of the Milky Way's formation and its interactions with neighboring galaxies. The study of pulsars is also expanding beyond our galaxy. With the increasing sensitivity of modern telescopes, astronomers are beginning to detect pulsars in other galaxies, including the Magellanic Clouds and even the Andromeda Galaxy. These extragalactic pulsars provide a unique perspective on how neutron stars form and evolve in different environments, from metal-poor galaxies to starburst regions where supernovae are more frequent. Looking ahead, the future of pulsar research is brighter than ever. The Square Kilometre Array, SKA, set to begin operations in the coming years, will revolutionize our ability to study pulsars, potentially discovering tens of thousands of new ones. The SKA's unprecedented sensitivity will allow scientists to explore the faintest and most distant pulsars, uncovering rare types such as intermittent pulsars that switch on and off unpredictably or nulling pulsars that occasionally stop emitting altogether. Space-based missions, like the proposed Lynx X-ray Observatory and the Laser Interferometer Space Antenna, LISA, will complement these efforts by studying the high-energy emissions from pulsars and detecting gravitational waves from neutron star mergers, respectively. These tools will provide a multi-messenger view of pulsars, combining electromagnetic observations with gravitational wave data to create a more complete picture of their behavior and interactions. In the grand tapestry of the universe, pulsars are threads that connect the smallest particles to the largest structures, from quarks to galaxies. They are reminders of the cosmic violence that creates them, the precision that governs their signals, and the mysteries they continue to hold. As we study pulsars, we are not only exploring the nature of stars and matter but also uncovering the deep connections that bind the universe together. Every pulse carries the echo of its creation, a message from a distant corner of the cosmos that invites us to listen, to learn, and to discover. The journey of pulsar research is far from over, and with each new discovery, we step closer to answering the most profound questions about our universe and our place within it. The story of pulsars is one of perpetual discovery, where every new observation and theory unlocks deeper layers of the cosmos. These enigmatic remnants of massive stars continue to challenge our understanding of physics, revealing phenomena that stretch the limits of human knowledge. As the pace of research accelerates, pulsars are emerging as a focal point for some of the most ambitious scientific endeavors in history. One of the most intriguing aspects of pulsars is their potential to probe the laws of quantum physics under extreme conditions. Deep within the cores of neutron stars, matter is compressed to densities billions of times greater than those found on Earth. At these densities, the behavior of particles is governed by quantum mechanics, yet this realm remains largely uncharted. Pulsars offer a unique opportunity to study the interplay between quantum physics and gravity, two of the most fundamental forces in the universe, which are notoriously difficult to reconcile in a unified framework. In particular, the interiors of neutron stars may contain exotic states of matter that challenge current models of particle physics. Some theories suggest that the cores of the most massive neutron stars could collapse into quark matter, a state where protons and neutrons break apart into their constituent quarks. Even more exotic is the possibility of strange matter, composed of strange quarks, which could be more stable than normal atomic matter. If pulsars harbor such materials, their discovery would revolutionize our understanding of the strong nuclear force, the force that binds quarks together in atomic nuclei. Observations of pulsar masses and radii, combined with sophisticated simulations, are helping to constrain these possibilities, pushing the boundaries of what we know about the fundamental building blocks of matter. Beyond their interiors, pulsars exhibit extraordinary magnetic fields that remain poorly understood. These fields are generated during the formation of the neutron star, amplified as the star collapses into a highly compact object. In magnetars, the most extreme type of pulsar, these magnetic fields can reach strengths of 10 superscript 1 Gauss, powerful enough to deform atomic structures and generate catastrophic outbursts of energy. Magnetar flares are among the most violent events in the universe, capable of releasing more energy in a single second than the Sun emits in 100,000 years. These flares produce intense gamma-ray and X-ray emissions, and studying them provides insights into the processes of magnetic reconnection and particle acceleration, phenomena that also occur on much smaller scales in our own Sunday magnetars may also hold the key to understanding fast radio bursts, FRBs. Mysterious millisecond-long bursts of radio waves that have puzzled astronomers since their discovery in 2007. Recent observations have linked some FRBs to magnetars, suggesting that their intense magnetic fields and dynamic environments could produce the energetic phenomena needed to generate these bursts. However, the exact mechanism remains unclear, and many FRBs, especially those originating from distant galaxies, exhibit behaviors that defy simple explanations. Could there be other types of neutron stars or entirely new astrophysical objects responsible for these signals? The connection between pulsars, magnetars, and FRBs remains one of the most tantalizing open questions in modern astrophysics. Pulsars also offer a unique window into the study of gravitational waves, ripples in spacetime produced by some of the most dramatic events in the universe. While detectors like LIGO and Virgo are designed to capture high-frequency gravitational waves from sources like black hole and neutron star mergers, pulsars allow us to study low-frequency gravitational waves from supermassive black hole binaries. Pulsar timing arrays, PDAs, which monitor the precise timing of millisecond pulsars across the sky, are sensitive to these slow, long-wavelength waves. By analyzing tiny variations in the arrival times of pulsar signals, astronomers can detect the subtle distortions caused by gravitational waves passing through our galaxy. Recent results from PDAs have provided tantalizing hints of a gravitational wave background, a faint chorus produced by countless merging supermassive black holes across the universe. The potential of pulsar-based navigation is another exciting frontier. Pulsars' precise and regular signals make them natural beacons for determining position and velocity in space, far beyond the reach of Earth-based systems like GPS. This concept, known as XNAV, X-ray navigation, has already been tested with NASA's NICER experiment, which demonstrated the feasibility of using pulsar signals to locate the International Space Station in orbit. In the future, pulsar-based navigation could guide spacecraft on interstellar missions, providing humanity with a galactic positioning system that operates independently of any planetary infrastructure. The search for new pulsars continues to uncover unexpected phenomena. Advanced radio telescopes, such as the Square Kilometre Array, SKA, and the Meerkat Array, are discovering pulsars in extreme environments, including the dense cores of globular clusters and the crowded regions near the galactic center. These discoveries are shedding light on the formation and evolution of pulsars, as well as the dynamics of the dense stellar populations in which they reside. The SKA, in particular, is expected to revolutionize our understanding of pulsars, potentially increasing the known population by an order of magnitude and revealing rare and exotic types of neutron stars that have so far eluded detection. Space-based observatories are also expanding the horizons of pulsar research. The Fermi Gamma-ray Space Telescope has uncovered a population of gamma-ray pulsars, many of which were invisible in the radio spectrum. These discoveries highlight the diversity of pulsar emission mechanisms and suggest that there may be entire classes of neutron stars yet to be identified. Proposed missions like the Lynx X-ray Observatory and the Cherenkov Telescope Array will further enhance our ability to study high-energy emissions from pulsars and their environments, offering new insights into the physics of particle acceleration and magnetic field dynamics. Even as we expand our observational capabilities, theoretical research is advancing in parallel, driving new insights into pulsar behavior. Simulations of neutron star mergers, for example, are revealing the complex interplay of gravity, magnetism, and nuclear physics that occurs during these cataclysmic events. These models are helping scientists interpret observations of kilonovae, the brilliant flashes of light produced by neutron star collisions, and the gravitational waves they emit. Such studies are not only shedding light on the formation of heavy elements like gold and platinum but also providing clues about the birth of new pulsars in the aftermath of these mergers. As we look to the future, the possibilities for pulsar research are as vast as the cosmos itself. These objects, born in the explosive deaths of massive stars, continue to illuminate the fundamental forces that govern the universe. From their role in testing the limits of general relativity to their potential as tools for interstellar exploration, pulsars are shaping our understanding of the cosmos in ways that were unimaginable just a few decades ago. Pulsars remind us that the universe is not static or predictable but a dynamic, evolving tapestry of matter, energy, and forces. They are the cosmic witnesses to events that have shaped galaxies, stars, and even the elements that make up life on Earth. As we continue to study these extraordinary objects, we are not only uncovering the secrets of the universe but also deepening our understanding of our place within it. Each pulse from a distant neutron star carries with it a message, a testament to the resilience of matter and the unyielding march of time across the vast expanse of space. In the end, pulsars are far more than just cosmic lighthouses. They are the ultimate paradox, remnants of catastrophic destruction, yet symbols of order and precision, ancient relics of stellar death, yet gateways to the future of science and exploration. Their study connects us to the most fundamental questions about the universe: how it began, how it evolved, and where it is heading. Each discovery about pulsars pulls back the curtain on the workings of reality itself, revealing the hidden dynamics of gravity, matter, energy, and spacetime. These enigmatic objects challenge us to confront the extremes. Their dense interiors harbor mysteries about the building blocks of matter, where the physics of atomic nuclei collapses into something new and exotic, something we have yet to fully comprehend. Their magnetic fields, so unimaginably powerful that they could distort the very atoms in our bodies, show us forces operating at scales that strain the limits of current science. Their relentless pulses, some spinning hundreds of times per second with atomic clock precision, are a reminder of the universe's capacity for order amid chaos. Pulsars are also storytellers, preserving the history of the cosmos in their timing, their location, and their behavior. They tell the tale of the violent lives of stars, the evolution of galaxies, and the interstellar medium that lies between. They show us how matter behaves when pushed to its absolute limits, how stars die, and how they continue to shape their surroundings long after their fiery end. Through their beams, they carry messages across the void, information that speaks to the interconnectedness of everything in the universe, from the microscopic quantum scale to the gravitational dance of entire galaxies. But perhaps most profoundly, pulsars inspire us to look outward and dream of what is possible. They have become tools of exploration, guiding us in our attempts to map the unseen forces that shape the universe. Their signals are being repurposed to navigate the stars, paving the way for humanity's future beyond Earth. They stand as cosmic milestones, marking humanity's ability to unlock the secrets of the universe with ingenuity, curiosity, and persistence. As we gaze deeper into the cosmos with ever more powerful instruments, pulsars will remain at the forefront of discovery. The next generation of telescopes, like the Square Kilometre Array, promises to uncover pulsars in far-flung corners of the galaxy and even in other galaxies, bringing new insights into the physics of neutron stars and their environments. Space-based observatories will reveal their high-energy secrets, allowing us to study the forces that drive their incredible emissions and perhaps even uncover entirely new classes of objects. The search for pulsars also pushes the boundaries of technology and computation. Advanced machine learning algorithms are already discovering pulsars hidden in vast datasets, uncovering faint signals that human eyes would never see. As our computational power grows, so will our ability to find and analyze pulsars, uncovering more of their secrets and opening new doors to understanding the universe. Ultimately, pulsars are not just astrophysical phenomena, they are mirrors of human ambition and ingenuity. They show us the power of asking questions, of looking beyond what we know, and of reaching for the unknown. They are reminders of the universe's capacity for both destruction and creation, for chaos and precision, and for revealing truths that transcend the boundaries of time and space. The pulsars we study today are ancient, their origins stretching back billions of years, but their significance will carry forward into the future. As we continue to explore and learn from them, we are participating in a journey that connects us to the stars and to the deepest mysteries of existence. Pulsars, in their steady, rhythmic pulses, remind us of the vastness of the universe, the resilience of matter, and the boundless potential of human curiosity. Their light will guide us, not just through the cosmos, but toward the answers to the questions that define our place in the universe.